Okay, so in this video, we want to answer the following question. Does the improper integral converge or diverge? And we have the integral from 0 to 1 of sine of x squared over x to the 5 over 2. Well, we have a finite interval, so if this is to be an improper integral, it has to be of type 2, so we have to have a discontinuity. Well, our discontinuity is fairly obvious. At 0, 0 to the 5 half is 0, and we have a division by 0, which implies a discontinuity. Well, how do we proceed? We have our function f of x. Can we get a guess as to this improper integral will converge or diverge? And the answer is yes. We'll provide a heuristic argument, and then we'll provide a rigorous inequality. And all you have to do is remember the well-known limit. As you let x approach 0, and look at the ratio of sine of x over x, this will give you a 0 over 0 case. If you use L'Hopital's rule, you'll get cos of x over 1, which is simply cos of x, and cos of 0 is 1, and so this limit is 1. And now think of what this implies. This is saying, as x approaches 0, sine of x over x approaches 1. So when x is very small, sine of x over x, so sine of something over its argument, will be very close to 1. So if x is very close to 0, sine of x over x is very close to 1. If you multiply through by x, the implication, of course, is that sine of x is approximately x. So we can simplify our function f of x quite nicely with this. And again, we're only worried about values of x that are near 0. This is where we have our discontinuity. Away from 0, everything else is fine, we have continuity. So we can look at the behavior of f close to its discontinuity, namely when x is close to 0. But x here is just a variable, right? What it says is, if the argument of sine is very small, sine of the argument is roughly the argument. Well, when x is very close to 0, x squared is very close to 0, and so sine of x squared is roughly its argument, x squared. And now we can simplify. 5 half minus 2 is 1 half. And if you prefer, that's just 1 over root of x. So we're saying very close to, and again, this is only when x is close to 0, but close to our point of discontinuity, the function behaves roughly like 1 over root of x. And if we integrate 1 over root of x from 0 to 1, we have seen similar integrals in the past. This will actually converge. So, with this intuition that our integral should converge, we want to bound f above by something that is also going to converge, which will give us a finite upper bound on I. And again, we will use here, to get a proper inequality, the idea of the tangent line to sine of x. Will give a slightly better statement than simply sine of x is roughly x. So look at the graph of sine, and again the point of interest is near 0. And we're only interested by sine of x between 0 and 1. So I'll stop there. We know that sine reaches its maximum value of 1 at pi over 2. Well, pi is larger than 2, so this is slightly larger than 1, so 1 will be roughly here. And you can look at the tangent line to sine of x at x equals 0. The tangent line happens to be simply y equals x. And again, we can perform a quick check. The slope of the tangent line is the derivative of the function at the point of tangency. The derivative of sine is cos. Cos of 0 is 1. Our slope is 1, check. And the tangent line touches the curve at the point of tangency. Sine of 0 is 0. 0 gives us y equals 0, check. So we have the right tangent line. And again, because sine is concave down, we can see that the tangent line is always above sine between 0 and 1. Therefore, the fact that x is between 0 and 1 implies that x is larger than or equal to sine of x, which itself is non-negative. And so we can take the reciprocal, but more interesting is this is true for any variable between 0 and 1. But if x is between 0 and 1, so is x squared. This is a direct consequence. Therefore, it is true that x squared is greater than or equal to sine of x squared, which in turn, of course, is at least 0. So we can use this inequality in simplifying f of x with a proper inequality. Right? If I just rewrite this backwards, 0 is at most sine of x squared, which in turn is at most x squared. And now we're good to go. So our function f of x, which equals the sine of x squared over x to the 5 over 2, will be at most, we keep the same denominator of x to the 5 over 2, and we replace sine of x squared by something that is larger, namely x squared. We can simplify as we did before. 5 minus 2 is 1/2. And now this is our g of x. But thinking of integration and the power rule, we will rewrite g of x as x to the power of negative 1/2. And now, as always, we will ignore the integral of f from 0 to 1 in favor of the integral of the much simpler function g. This is once again an improper integral. At 0 we have the root of 0, which is 0, so we have a division by 0. The function therefore does not exist there and gives us a vertical asymptote. So as always, we first avoid the discontinuity, and I'll rewrite 1 over root of x as x to the negative 1/2. And we have to let t approach 0, and as always, in the case of a lower bound of integration, we have to let t approach 0 from the right. And now as t is positive, from t to 1, our function is continuous, and so we can use the fundamental theorem of calculus. By the power rule, we add to our exponent 1. Well, negative 1/2 plus 1 is 1/2. which is simply root of x. And we divide by 1/2, but if you divide by 1/2, same as multiplying by 2. And so our antiderivative is 2 root of x. And we evaluate from t to 1. So 2 root of x, replacing x by 1 is 2 root of 1, which is simply 2, as the root of 1 is 1, minus the function, replacing x by t, which gives us 2 root of t. And now we have a very simple limit. As t approaches 0 from the right, root of t will approach the root of 0, which is 0. This term vanishes, and we have in the end 2. So this integral converges, which will prove that the integral of f also converges. Again, our function is non-negative, so the integral will also be non-negative. But this function is smaller than g, and so the integral of the smaller function will be smaller than the integral of the bigger function, which you can write as simply 1 over root of x. But even though we have here an improper integral, we have just found that this integral converges and is exactly equal to 2. So what is our conclusion? If you visualize the sequence of inequalities onto the real line, the improper integral, which is rather nasty, lies somewhere between 0 and 2. So the improper integral is finite, therefore it converges. And we're done.